Hello again. This is Math 2, 115, coming to you from the College of DuPage. And the title of this lecture is Counting Subsets of a Set, Combinations. Remember to be an active learner as you watch this video. Consider the following problem. Suppose 5 members of a group of 12 are to be chosen to work as a team on a special project. How many distinct 5-person teams can be selected? Now, we're going to answer this very question later, but you can generalize this to say, given a set S with n elements, how many subsets of size R can be chosen from S? The number of subsets of size R that can be chosen from S equals the number of subsets of size R that S has. Each individual subset of size R is called an R combination of the set. So if n and R are non-negative integers and R is less than n, then an R combination of a set of n elements is a subset of the n elements itself. And in fact, although we're going to come up with a formula for this, it's useful to often think about it in this context. And this is the notation we use. So this symbol, and the way we read that is n choose R, denotes the number of subsets of size R, or R combinations, that can be formed from a set of n elements. We're counting the number of these subsets. And many, I know we talked about this before, but there's different notations. My favorite notation is probably this one, n choose R. That means how many ways can you choose a subset of size R from n. But there are many different notations. Let's consider this example. So we have a set of 4 people. A, B, C, and D are their first initials. And given that set, each subset of size 3 is a 3 combination. Let's list all the 3 combinations. Well, if we leave Ann out, we get this one. If we leave Bob out, we get this one. If we leave Sid out, we get this one. If we leave Den out, we get this one. So the answer to this problem is 4. And so use this result to find 4 choose 3. Well, 4 choose 3 is going to be 4 because of that. In how many ways can the people in the set form a committee of size 3? Well, the answer there is also 4. It's the same thing because you could say those are the 3-person committees, and those are all distinct. Notice that order doesn't matter. In fact, that's where we're going next. There are 2 distinct methods can be used to select R objects from a set of n. In an ordered selection, it is not only what elements are chosen, but what's the order in which they are chosen. 2 ordered schemes are said to be the same if the elements chosen are the same n, they're chosen in the same order. An ordered selection of R elements from a set of n elements is an R permutation of the set, and we've already talked about those a bit. In an unordered selection, like we just were talking about here, on the other hand, it is not only the identity of the chosen elements that matter, it is only the identity of them. 2 unordered selections are the same if they consist of the same elements, regardless of the order in which they were chosen. An unordered selection of R elements from a set of n elements is the same as a subset of size R, or an R combination of that set. So let's do an example here. How many unordered selections of 2 elements can be made from this? And that would be 4 choose 2. Okay, well, you start thinking about how many different ways can you choose 2, and you just can list them out getting this. So 4 choose 2 is 6. Now, when the values of n and r are very small, it's reasonable to calculate this just using this complete enumeration method here, listing all possibilities. But when it's large, it's not really feasible. So what we're going to do is the values of n choose r can be found by a somewhat indirect but simple method. We're going to have an equation, and we're going to solve for that equation. Now, the derivation, I think, is useful for you to understand, but the important thing is to understand the result. Okay, so when we wrote all 2 permutations of this set, and we want to find an equation related to the number of 2 permutations and the number of 2 combinations, and solve this equation. So anyway, here's what we do. We know, according to some stuff we studied before about permutations, the number of permutations is 4 factorial over 4 minus 2 whole factorial. We cancel out the 2 factorials and we get 12. Now, in the act of constructing a 2 permutation, can be thought of as a 2-step process. We choose the 2 elements and then we choose an ordering for them. That process can be thought about as a tree. And so if we went through this tree here, we write the 2 combination of that, and then we obtain ordering, and these are what we get for our results. And so the number of ways that we can do this is, first part is 4 choose 2, and the number of ways in step 2 is 2 factorial, okay, for each one of those. You see there's 2 times 1 for each one of those. So you see this is what we have. 4 permutations taken 2 at a time, or a 2 permutation of 4, is 4 choose 2 times 2 factorial here. And we can solve this equation just plugging in numbers, and we can get 6. Now if we use this reasoning in a broader example, the number of r permutations of n elements would be n choose r times r factorial. And so we can solve this for n choose r, and if we do, we get this formula. N choose r is equal to n factorial over r factorial times n minus r whole factorial. And that's the result you want to remember. So here's the formula that you want to remember for n choose r. And here we talk about that also works for 0 and 1. And so that's going to be for any n bigger than or equal to 0. And for all non-negative integers n and r less than or equal to n. Okay, this is the original problem we started talking about at the beginning of the section. So consider the problem of choosing 5 members from a group of 12 to work as a team on a special project. How many distinct 5-person teams can be chosen? Well, it's 12 people choose 5, or it's 12 choose 5. You use the formula that we have. You cancel out common factors and so on and so forth. You multiply together the remaining and you get 792. Thus, there are 792 distinct 5-person teams. Now suppose 2 members of the group of 12 insist on working as a pair. I've had that happen in class. Any team must contain either both or neither. If you do that, how many 5-person teams can be formed? Well, a team that has both A and B in it looks like this. You have A, you have B, and then you have 3 blanks, and you can put other people in there. And so you see you have 3 slots to fill with the remaining 10 people. Well, 10 choose 3 then, and since this is a team, it didn't matter which order is 120. So we get 120 that have both A and B on them. Now, a team that has neither A nor B looks like this, but what happens is that A or B can't be there. That means we have 10, and we're choosing 5 people this time. So 10 choose 5 is 252. Now, because the set of teams that contain both A and B is disjoint from the set of teams that contains neither A and B, so what we have is, by the addition rule, that we add those 2 numbers together, and we get 372. And here's another picture that talks about how you can arrive at that conclusion. Now this is a little bit different. Suppose 2 members of the group don't get along. I've also had this happen in class and refuse to work together on a team. How many 5-person teams can be formed? Call the people who refuse to work together C and D, just to call them something. There are 2 different ways to answer the question, but both have the same answer. One uses the addition rule and the other uses a difference rule. To use the addition rule, partition the set of all teams that don't contain C and D into 3 subsets, as shown in this figure over here. Okay, so because any team that contains C but not D contains exactly 4 other people of the remaining 10 in the group, so 10 choose 4 is 210. So you see that teams that contain C but not D is 210. Similarly, teams that contain D but not C is also 210. Now we have to now calculate teams that contain either or neither C nor D. Well, that means that we have 10 people, but this time we're choosing 5 from there. We get 252. We're going to add all these numbers together, and what we will get is 672 if we add those numbers together. An alternative solution by the difference rule is based on the following observation. The set of all 5-person teams that don't contain C and D equals the set difference between the set of all 5-person teams and the set of all 5-person teams that contain both C and D. This may be easier for some of you to think about it that way. And this just says what I did. So we have this number minus this number, and that's again equal to 672. And this is showing that yet again. Before we begin the next example, remark on the phrases at least and at most is in order. The phrase at least in means in or more. The phrase at most in means in or fewer. Okay, so let's suppose you have a group of 12 consisting of 5 men and 7 women. How many 5-person teams can be chosen that consist of 3 men and 2 women? Think about this as being 2 steps. Choose the men, then choose the women. So how many ways can you choose the men? 5, choose 3, times, how many ways can you choose the women? 7, choose 2. Now there's a lot of calculation involved here, and I expect you to be able to use the calculation or use your calculator, but the answer is 210. Problem B says, how many 5-person teams contain at least 1 man? Now the question here can be answered either by the addition rule or by the difference rule. Again, a lot of times the difference rule may be cleaner for some students. And certainly it is shorter, okay? So here's what we will do then, is by the difference rule, what we're saying is the number of teams with at least 1 man is equal to the total number of teams minus the teams that do not contain any men. Well, the total number of teams is 12, choose 5. And we're going to subtract off the number of teams that don't have any men, and that is 7, choose 5, because you're really just picking it totally from the women. So if you do that calculation, you get 771. And the reasoning is summarized down here as well. Same answer, different approach. And here you could say, oh, how would you get 1 man and 4 women, 1 man and 2 men and 3 women, and so on and so forth. And those are all disjoint sets because they have different compositions. So that means you add their probabilities together. It's multiplying all those. This is actually very computationally intensive, but you do get 771. And here is a picture that may help some of you understand that. Pause this if this picture is useful for you. And here we were supposed to talk about the set of teams containing at most 1 man. So you see this is the number of teams without any men, or the number of teams with exactly 1 man. And so this is how we get the teams with no men. You pick no men from here, that's going to be a 1. And you pick 5 from the 7 women, or you pick 1 man from the 5 times 7, choose 4. There you're choosing 4 from the women. And if you look at that reasoning and do those calculations, you get 196. Poker hands also are frequent source of problems here. Poker hand is played with an ordinary deck of 52 cards and various kinds of cards, and this is in fact the order in which these cards are hands are evaluated. So we have royal flush, straight flush, so on and so forth. And if I give you a test question on this, I will probably, give you this information just because you all don't know how to play this brand of poker. In fact, these days, for the most part, it's Texas Hold'em, and it's kind of a different thing anyway. Okay, so, but now we can do problems with these, and I think we're going to talk about finding the probability of one pair. But let's go see what the problem really is. Well, actually it is two pairs. I'm sorry. How many poker hands contain two pairs? And that means you have, for example, two aces and two deuces and another card. And then in part B, we'll worry about part B later after part A. Okay, so what we're going to do is consider, and we're going to think about forming a hand of two pairs as a four-step process. We pick what are the two denominations for the pair. Now I talked about an ace and a deuce. There could be others, but that's what you do. Then you choose two cards from the smaller denomination, and then you choose two cards from the larger denomination. And you realize that the two cards from the smaller denomination cannot overlap with the two cards from the larger denomination because they have to be different, because otherwise you would have three of a kind. And then last, we have one more remaining card, because you see we get two here and two here, so this is the fifth card in the poker hand. Okay, so here's what you do. You first choose the denomination. There are 13 cards ranging from the ace all the way up through the king, and you're picking two of them, so this is 13, choose two. Then what you're going to do is you're going to pick the two cards with the smaller denomination, so that is 4, choose 2. There are 4 suits, you're choosing 2 of them. And then you're going to choose cards from the larger denomination. There are 4 cards, and you choose 2 of them. Then you have to choose the remaining card. Now you have to realize how many cards have I used already, and you see that there are going to be, you see you've got 4 there, and so what you're going to have is this is going to be the way we're choosing this other card. Now you can't match this denomination, and you can't match this denomination, and so that, and also there's 2 suits, so there's a lot of cards eliminated, so you have 44 remaining cards to choose from, and you choose 1. So we write all that out, we do quite a calculation, and we get there 123,552 ways to do that poker hand. If a 5-card hand is dealt at random from an ordinary deck, what's the probability that it contains 2 pairs? Well, we already figured out the numerator. This is how often does that happen. So all we have to really do is say, how many different ways can we get a 5-card hand? And we'll divide this number into, we'll divide, this number will be the numerator, this will be the denominator. And this is 52, choose 5. You should practice calculating this, but this is what you get. And so we take the 123,552 divided by this number, and we get that that happens about at 5%, a little less than 5%. Here's very much of a computer science problem. How many 8-bit strings have exactly 3 ones? So you have 8 slots to fill with zeros or ones. We need to pick where are we going to put the ones. Well, how many different ways could you choose places to put the ones? Well, there are 8 slots, and you're choosing 3, so it's 8, choose 3. You do the calculation, you get 56. And so that's the number of ways, because we're just going to be putting zeros in the other slots. We can also talk about permutations of a set with repeated elements. Consider the various ways of ordering the letters of the word Mississippi. Now, Mississippi has 4 I's, 4 S's, 2 P's, and you can't tell the difference between them. So if you have multiple ones landing in a slot, we cannot distinguish between those different things of the letters. Okay, so what we need is we have 11 letters and we're placing in these slots. And here's 4 steps. Choose a subset of 4 positions where we're going to put the S's, 4 positions where we're going to put the I's, 2 positions to put the P, and then we have 1 for the M. Okay. So we will go through and we will calculate that. So we do, we had 11 spaces, 4 places to put the S is this, 11 choose 4. Now after we've got the S's in place, now we're going to look at the I's, and this is 7 choose 4 because there's only 7 spaces remaining. And then we look at the remaining 3 spaces and we pick 2 of those for P, and then we have this. So you see it's the product of these 4 steps. If you do the calculation, you get this, 34,650. Now let's generalize this result with a theorem. Suppose you have a collection of n objects of which n1 are of type 1 and are indistinguishable from each other. This is like the I's. And n2 are of type 2 and are indistinguishable from the other. This is like the P's, and so on and so forth. So you have a bunch of things that are indistinguishable from the other. Then you can go through the same argument as a proof, but if you simplify this, what you get is, it is n factorial over n1 factorial plus, times n2 factorial times n3 factorial dot dot dot, thank goodness, dot dot dot, n sub k factorial. And n1, 2, 3, if you add up all those n sub k's, they add to n. Okay, let's continue with some advice about counting. Some students will ask, how do I know what to multiply and when to add? Well, when I use the multiplication rule and when do I use the addition rule, that's some other questions students might ask. There aren't easy answers, but it's helpful to make a list of the items you need to count and how you want to count them in a systematic way. Then you construct a model for doing this. And one of the most common mistakes that happen when students do this is they count certain possibilities more than once. They double count. Here's a problem dealing with double counting. And we're going back to the problem of a group consisting of 5 men and 7 women. How many teams of 5 contain? At least 1 man. The group you're picking from has 5 men and 7 women. Okay, and you might say, well, I'll pick the man and then I will pick the woman and multiply this. Now, this is not correct because you didn't really implement 2 steps here correctly. So suppose the men are A, B, C, and D, and E, and the women are F, G, H, I, J, K, and L. Okay. So the outcome of step 1 was this one, and the outcome of step 2 is this one. But you see you're double counting. In this case, the team would be this. But another outcome would be Ben and this, which gives this. This one team, given by the 2 different branches of the possibility tree, is counted twice. So the best way to avoid mistakes is to visualize the probability tree corresponding to the use of the multiplication rule and the set partition that corresponds to the use of the addition rule. Check how your division works by applying it to some actual data. Do a small example. It often helps to say, am I counting everything? And am I counting anything twice? In closing, now more than ever, time is precious. Each day must count. Do the math, it'll make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.